Here's a diagram of several of the dwarf planets in our solar system, accompanied by their moons. So one you're definitely familiar with is Pluto. So Pluto's a dwarf planet, and it has a moon, Charon. The Earth's moon, Luna, is shown in this diagram. So you can see all of these dwarf planets are smaller than our own moon. Ceres, discovered by Giuseppe Piazzi in 1801, that's within the asteroid belt. And so all these other Makemake, Haumea, Eris, they're all orbiting beyond the orbit of Neptune. So they're often referred to as trans-neptuniun orbits. They're also referred to as KBOs. A KBO stands for a Kuiper Belt object. Now, the Kuiper Belt is the solar system's, it's a dense region of small objects that orbit around the sun, roughly in the plane of the ecliptic, and it's not much unlike Saturn's rings. The whole solar system, in its way, has its own belt. And this belt is the Kuiper Belt, and it begins around the orbit of Neptune and extends to about roughly 50 astronomical units. So it goes from about 35 AU out to about 50 AU. And so you can see it here. There's the KB, the Kuiper Belt, all of that area. There are thousands, perhaps tens of thousands or more objects that have been identified within the Kuiper Belt. It's a source of a lot of comets. There's some gravitational interactions that can disrupt the orbit of any one of these objects and end up making it deviate from its path and come into the inner solar system. A lot of comets come from the Kuiper Belt. Here you can see the orbits of the dwarf planets. Most of them appear to orbit in a circular path. You can see probably Eris has the most elliptical, they all have elliptical orbits, but Eris has the greatest eccentricity. I want you to notice one more thing here. If you look at the orbit of Pluto and the orbit of Neptune, they cross paths. In fact, I'm not sure at this very moment which is farther away from the sun, whether it's Pluto or Neptune. I'd encourage you to investigate and look that up. There's another source of comets that lies beyond the Kuiper Belt, and instead of sitting in a ring or a belt or in a plane, there's a region known as the Oort Cloud, which is more of a spherical distribution of small bodies and comets, and that orbits at a greater distance, starting from about 5,000 AU out to 100,000 AU. It's easy to identify if a comet came from the Oort Cloud. If a comet orbits in the plane of the ecliptic, then there's a good likelihood that it came from the Kuiper Belt, although I suppose an object that was disturbed and came in from the Oort Cloud, it could also orbit in the plane of the ecliptic. But if there's any comet that orbits with a highly exaggerated, in a highly exaggerated plane like this, then chances are it came from the Oort Cloud. And the other way to tell if it came from the Oort Cloud is if it has a very long period. After all, we know from the law of harmony that period squared is proportional to the average radius or the length of the semi-major axis cubed. So if it has a larger average distance, it's going to have a longer period. In fact, a lot of comets that come from the Oort Cloud, you won't see them return in a lifetime. But the period for some of the comets that come from the Kuiper Belt can be less than the length of a lifetime, so you might see some of these comets return. Okay, let's do an example problem. Oh, and just here's one more diagram showing the relationship between the Kuiper Belt and the Oort Cloud. Notice that we only show in this diagram the orbit of the larger planets, sometimes referred to as the Jovian planets. So there's Jupiter, Saturn, Uranus, and Neptune. And then beyond that, the Kuiper Belt, anything else would be a trans-neptuniun object. The inner planets orbit too close together to show with any reasonable spacing in here. So those are sometimes called the terrestrial planets, Mercury, Venus, Earth, and Mars. And then Saturn through Neptune are called the Jovian planets. Let's say we had a comet that orbited in an elliptical path, and it has a period of 100 years. And let's say we also know that at perihelion, its distance at closest approach to the Sun is 1.2 astronomical units. So that would put its orbit somewhere in between the orbit of Earth and Mars. Can you figure out what's the distance at Aphelion? Well, based on the law of harmony, we should be able to figure this out. Now, the law of harmony can be stated as the length of year for any one object that orbits the Sun compared to the length of its semi-major axis, period squared, radius, or semi-major axis cubed, is the same ratio for a second object. And when you express the law of harmony in this way, it doesn't matter what units you use. You can express period in years and orbital distance in astronomical units. However, this comes from an equation that says period squared is equal to 4 pi squared over gm times average radius cubed. And when you express it this way, as long as we're going to use the known constants like 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, or the mass of the Sun, a solar mass, is about 1.99 times 10 to the 30th kilograms. If we're going to stick to units in the MKS or metric system, then the period has to be in seconds and the radius has to be in meters. So it'd be helpful to know how many seconds are in a year. You can multiply 60 seconds in a minute times 60 minutes in an hour times 24 hours in a day times 365, actually 365.24 days in a year. It's not a whole number of rotations that fit into one revolution for the Earth. This is why we have leap year almost every 4 years, and then on the century we don't count those years as leap years. And anyway, if you multiply all this out, you can see what you get. 3.15 times 10 to the 7th seconds is equivalent to a year. Well, that's close enough to 3.14 that is pretty memorable, and you won't be too far off if you just say, I can commit to memory that there are pi times 10 to the 7th seconds in a year. So that's helpful. So let's make that conversion. Then this would be 3.15 times 10 to the, 100 is 10 to the second. So, yeah, if it orbits with a period of 100 years, it orbits with a period of 3.15 times 10 to the 9th seconds. And then you probably know that 1 AU is 1.5 times 10 to the 11th meters. Okay, let's figure out then what the distance is at Aphelion. All we need to do is rearrange this equation. So the length of the semi-major axis cubed is equal to, how about this? We can make this simplified. How about, since all these quantities here are a constant, let's figure out that constant is equal to. So before we rearrange the equation, let's express it as period squared is equal to some constant times semi-major axis cubed. That constant would be equal to 4 pi squared over gm. So the reason we say it's a constant is because we're referring to objects that orbit around the Sun. So g is a universal constant, and if we limit ourselves to a discussion of satellites of the sun, then m is the mass of the sun, like I say, 1.99 times 10 to the 30th kilograms. Well, if you grab a calculator and work this out, you find that the constant is equal to 3 times 10 to the negative 19th, and the units must be seconds. Seconds squared per meter cubed. Okay. So then if we rearrange the equation, then the length of the semi-major axis should be equal to the cube root of period squared divided by this constant. So in our example, the period was 3.15 times 10 to the 9th seconds. We've got to square that, divide it by the constant, sometimes called the solar constant, 3 times 10 to the negative 19th seconds squared per meter cubed. You see what happens with the units. The seconds are going to get squared, and so they'll cancel out, and we'll be left with the inverse of cubic meters, which of course will give us meters as a final result once we take the cube root of everything. So if you work this out on your calculator, you find that the length of the semi-major axis is 3.21 times 10 to the 12th meters. Let's draw a picture of this. There's the sun. And in this case, it's not much of an exaggeration to draw the orbit of the comet as being highly elliptical. And so we are told that this distance is 1.2 AU, and then we just found that this distance is 3.21 times 10 to the 12th meters. So the length of the whole major axis is double that, so 6.42 times 10 to the 12th meters. If we divide that by 1.5 times 10 to the 11th meters, we can convert it to AU, and that's equivalent to 42.8 astronomical units. Okay, so R1 added with R2 has to be the length of the major axis. So R2 is 2A minus R1. So in our case, R2 is 42.8 astronomical units minus the given value from this example problem of 1.2 astronomical units. And so we've got it. The distance at Aphelion is equal to 41.6 astronomical units. So the question is, where's the likely origin for this comet? Is it in the Kuiper Belt or the Oort Cloud? Yeah, it's clearly an object that came from somewhere within the Kuiper Belt.